All right, so we have this kid, Ethan. He's trying to drag a bag of grass from his garage to the street on the evening before garbage pickup day. That's a pretty massive bag of grass. 160. It's like it's like 180 pounds or something ridiculous like that. Yeah, it's like yeah, it's okay. I borrowed this problem from a colleague, so I'm a little surprised. But let's draw that free body diagram. So we've got a normal force, we've got a weight force, we've got a friction force, and we've got an applied force right here. Once again, let's go ahead and get the weight. So the weight of this bag is going to be 80 times 10, which is going to be 800 newtons. And again, let's be clear. What I'm saying here is that I have m times g, and also balancing forces vertically. We know that the normal force will balance the gravity force. So the effect here is that we're going to get that the normal force is also equal to 800 newtons. So Ethan is unable to get this bag moving. So we want to know what the static friction force is that opposes his pull. So we know the applied force minus the friction force balance because the bag doesn't move. He's pulling with 150 newtons, and the friction balances that. So what this tells us here is that the friction force is in fact equal to 150 newtons. And I'm going to add one little thing here. It is a static friction force since the bag is not moving. All right, so what we want to know is how hard does Ethan need to pull to get the bag moving? So to that end, we're going to calculate the maximum static friction that can keep up with the pulling force. So that's going to be mu static times the normal force. That's going to be 0.3 times the 800 newtons that we got here. And so that's going to give us 240 newtons of maximum possible friction force. So I'm pulling the thing. I have the maximum possible friction acting on it, and those should balance for it to be on the verge of moving, but not quite. So we're going to have the applied force is fighting the maximum possible friction. So we're getting Fa equal to 240 newtons. Now I know a lot of you in doing this on the test might calculate this and leap straight to this answer here, and I'm actually fine with that. Okay, so Ethan alone can only provide 150 newtons of force, so his brother comes out to help him. We want to know how hard his brother will have to pull to get the bag moving. So let's go ahead and draw a new free body diagram and solve that. So we have the normal, we have the weight, we have Ethan, and we have Ethan's broski right here. And we have this friction force right to the left, or pointing to the left. So here's what we're going to say. Ethan's force and his brother's force minus the maximum possible friction will just barely balance. So we're going to have 150 plus whatever force his brother applies. And opposing that is this maximum friction. And so when we actually solve, what we're going to end up getting is that the force that his brother applies is going to be 240 minus 150 newtons. So we're actually getting that his brother applies a 90 newton force. All right. Lastly, once the bag starts moving, his kind of mean brother jumps on top of the bag, and we want to know the maximum value of the coefficient of the friction for Ethan to be able to pull the bag. So here's what we're going to do. Let's kind of just take this bag and the brother. Okay, Larry, he's really happy. We're going to take this as just total mass equal to 80 plus 20, which is 100 kilograms. So we'll take our new free body diagram. I'll actually just take it from here. And we'll just move this little label down to the bottom. But we're going to be careful on how we label our free body diagram. So just to be clear, the gravity force is going to be 100 times 10, which is going to be 1,000 newtons. So we have the normal force minus 1,000 newtons equals 0. So Fn is going to be 1,000 newtons. Okay, this is going to be useful because what we also know is that the applied force minus the friction force has to balance at constant velocity. So we know the 150 Newton force minus the force of friction equals 0. So we know the friction force is 150 newtons. Okay, let's combine some of these ideas. So we know this, and we know the friction force. So using the friction formula, we know that the friction force equals mu kinetic times, we know the friction force equals mu kinetic times the normal force. So working with this, we have that the 150 Newton friction force is going to be mu k times the 1,000 newtons right here. And so the coefficient of friction is going to end up being 0.15 when we solve. All right, I just want to clean up that little answer right there. I just don't like the way it looks. So there we go. So that's our final answer for page number 2. And we'll take a look at the third page in the next one.